Thank you, Yunfeng. Uh, Hello, I am Arseni, graduating PhD student at the PFL, co-advised by Katrina Argirak and George Candia. I will present to you Vigor, a framework for practical verification that requires no verification expertise. Wouldn't it be great if you could quickly write system software and have it verified? Take an afternoon, write a little server, push a button, and here comes the formal proof that it will never crash, is memory safe, and best of all, functionally and semantically correct. With Vigor, we enable this for specific domain of software network functions. Network virtualization holds the same promise as machine virtualization, and networks are being virtualized by the day. But operators of critical network infrastructure are still reluctant to embrace it due to the infamous unreliability of software. And adopting formal verification for development of such software has a steep learning curve, and plus developers have little time or interest to study formal verification. Vigor provides verification agnostic network function developers practical way to mechanically verify their NF. To us, a verification framework is practical if it has these three features. It's push button, meaning it requires zero human effort and zero verification expertise. Pay as you go, in that it supports incremental verification with incomplete specifications. And full stack, meaning that it verifies not just the NF, but the whole software stack down to the operating system and drivers. Let's try to understand these three properties better. First, push button or zero human effort and zero verification expertise. We strongly believe that formal methods will never have significant impact until they can be used by people who don't understand them. A lot of work has gone into making verification of system software possible, and it still introduces 5 to 10-fold increase in development effort, which hurts the very advantage of software, namely agility and productivity. The time has come for verification tools that can automatically construct proof of correctness without assistance from developers, and this is what the push button is about. Second, pay-as-you-go is about being able to verify one of properties described by incomplete specifications without requiring the entire system to be specified. For instance, if all you want to check is whether a load balancer generates any response to a heartbeat packet, would you rather write the 3 lines on top or the full spec shown below? A practical verification tool should be able to verify the 3 lines without any additional spec. Third, full stack is about verifying the whole software stack. A network function typically runs on top of a packet processing framework and, of course, an OS and a NIC driver. The correctness of 3,000 lines of code NF is only as perfect as the correctness of the stack it runs on. And the packet processing framework and the NIC driver are more than an order of magnitude bigger than the NF. And the Linux kernel is 4 orders of magnitude bigger. That's a lot of code and possibly a lot of bugs. A correctness guarantee of application running on an unverified stack is practically worthless. Vigor is a framework for push-button verification of a full stack of software network functions in a pay-as-you-go manner. I will present today the main ideas behind Vigor, focusing on the design of the push-button aspect and the pay-as-you-go feature. I will conclude with highlights from our evaluation and encourage to read our paper for the many details that I cannot include in this talk. I'll start with the push button, but first, let me clarify what we mean by a network function. This is the core of a network middle box, like a NAT, a firewall, or a load balancer, or traffic policer. If you think abstractly of the code of a network function, it essentially consists of an infinite event processing loop that manipulates packet headers, stores and retrieves the data from data structures, and makes decisions about the fate of the packet. The code this code I show as boxes, while other parts of the NF code are relatively complex because they involve non-trivial iteration and intricate memory traversals. I show them as circles. These typically implement data structures such as a queue or a hash table. The code that in the NF can be easily grouped into NF logic on one hand, and a set of data structures on the other hand that can be organized into a library. And often different people develop these parts. NF developers write the NF logic, and they rely on the library of data structures, just like they'd use libc or Boost. They are professionals, but they have no verification expertise. library developers implement and optimize data structures and generally maintain the library of NF data structures. Unfortunately, if we wanted to verify an NF, there is no single verification technique that can handle the intricate code of the library while also being usable by someone who doesn't know verification. But if we cannot find two, let's use, if we cannot find one, let's use two. A different technique for each part. On one hand, exhaustive symbolic execution can prove some stuff. It is easy to automate, but it can handle pointers, infinite loops, and other such things that appear in the implementation of data structures. On the other hand, there is theorem proving, which is much richer and can prove pretty much anything, as you've seen on the previous talks, as long as the user is a verification guru. So exhaustive symbolic execution is just right for verifying the NF logic, while theorem proving can verify the library of data structures. In Vigor, we use theorem proving on the library of data structures to produce semantic contracts for the library interface, thereby formally guaranteeing that the library methods do the correct thing, when on the other hand we use the tweaked form of exhaustive symbolic execution to obtain all the paths through the NF logic in the form of symbolic traces. So we've used one technique for the data structures and another one for the NF logic. Now, here is the hard part. How do we combine the universe of symbolic path conditions from the traces with the universe of inductive data types and separation logic from the contracts? Stitching this together is one of our main research contributions. The challenge here is the huge gap between these two universes. Let me try to convey the intuition with an analogy. The symbolic trace contains calls made by the NF logic to the library API. I show each API call as a dot, and color of the dot corresponds to the color of the contract for that call. In this analogy, I show each API contract as an English word. The symbolic trace serves as a skeleton to thread together the API calls and turn the trace into a sequence of contracts. This already gets us closer to figuring out the semantic meaning of the trace, but we are not done yet. In our analogy, the word sequence doesn't quite form a meaningful sentence yet about what the NF says on the execution path corresponding to the trace. Vigor inserts so-called transition lemmas to form a proper sentence. In doing so, it takes into account the context of each call and a set of rules specific to each data structure. The result can now be passed to a proof checker, which verifies whether the NF says or does what it is supposed to say or do on this particular execution path. And Vigor repeats this for every symbolic trace that exhaustive symbolic execution produced. If all the traces verified, that means that on every possible execution of the NF, it does what it is supposed to do. In other words, we have a proof of correctness, and the NF developer did nothing but push a button, and the Vigor did all the rest. Correctness is always defined relative to a specification. Who writes the specifications for the NFs? Typically, this would be the usual standardization bodies, like IETF writing RFCs or IEEE formulating the network standards. Translating, sorry, a bug. So we see we didn't verify the clicker yet. If you design a system, you can also specify and be an author of a specification. Like, for example, Google team has specified the maglev load balancer should what the a load balancer that they could call a maglev should do. But so the problem here is, you may have glanced on the next slide. Vigor tied together this contract into a meaningful sentence and checked it against the spec. But what if the NF code and the specification use different abstractions? In our analogy, what if the NF speaker speaks English, but the specification may say exactly the same thing, but it is in French or German or Russian? Translation automatically, between the two sets of abstractions automatically is hard to get right. But what if there is a lingua franca, a common set of abstractions that are usable both for specifications and implementations? Well, let's take a look. When IETF formulates their RFCs, they talk about flow tables and protocol headers. When IEEE defines MAC learning, they talk about a MAC table. When Google describes their maglev design, they talk about a connection table. Aha, these are really just maps from keys to values. And what about the implementation code? It uses hash tables, which are the data structures to implement these maps. So our observation is that, yes, there exists a lingua franca, and its vocabulary is that of the standard NF data structures. In other words, in the domain of network functions, specifications and implementations tend to use the same abstractions. This is one thing that is great about the NF domain. And Vigor can therefore both understand the spec and verify the code, the implementation that does the same thing that the spec describes. And this insight enables push-button verification. By automating the verification process, Vigor reduces the usual development overhead of 5 to 10x down to about 50%, which is roughly what it takes to write a complete specification. The NF developers does virtually nothing extra. So far, we've seen how Vigor reduced the developer's burden with push-button verification. Now, I'll explain how it reduces the specification effort too. The overhead consists of a substantial fixed cost of writing the entire spec plus a variable cost of formulating the property of interest. We want to reduce the fixed cost. For instance, when you want to check a specific property of the NF, you shouldn't have to write the complete spec of its behavior. Or here comes the pay-as-you-go approach that allows you to pay the minimal fixed cost, and immediately be able to start verifying properties and then develop the spec incrementally as you go. Perhaps not even write it fully and just stop at a couple of properties of interest. To illustrate the difference between the full spec and a partial one, here is our formalization of the stateful firewall. It is written in our dialect of Python, but you don't have to read it because here is, in contrast, the example of a partial spec that only checks that the packet coming from the external network corresponding to an existing flow can get through. To make the partial specifications possible, we use the Python pass keyword to let the user ignore a particular class of events that are not of interest, and ellipsis that lets you ignore the values that are not important for the property of interest. With these pieces in place, let's see the typical workflow from an NF developer point of view. Say you want to implement a firewall and verify its correctness. Write the firewall code using the data structures from the library provided by Vigor. You can use pay-as-you-go to improve your performance in development. All the specs are in Python, so most of the people should be familiar with that. And next, get the official spec to verify your code does the right thing. Anytime you run our tool, Vigor, with a spec, partial or full, it constructs a refinement proof that the code provides the specified property, verify the proof when you are happy. But if the implementation does not match the spec, then Vigor provides debug support, essentially an execution trace that demonstrates the discrepancy. This is all a network function developer needs to know. So we saw push button and pay as you go. The third and final component of practical verification is full stack, namely verifying all the software that runs underneath the NF. I don't have time to talk about it, but the main idea is that we automatically verify just the parts of the stack that are relevant to the specific NF. Vigor soundly ignores framework, OS, and driver code that are not relevant to the verified property, and specifically, symbolically executes the rest, the code that is relevant. There is lots of technical details, so please see our paper for the details. To recap, Vigor adapts to the normal NF structure and current development practices. NF code naturally splits into NF logic and underlying data structures, and Vigor leverages the separation and analyzes the two parts differently, then stitches the results into a global proof. There is a common language, a common set of abstractions used to implement and specify network functions, and the interface and contracts for the Vigor library of data structures are therefore expressed using the same abstractions. And this enables Vigor to do mechanical verification of NF semantics and in a fully automated manner. For the cases when Vigor's users don't want the fixed cost of writing a full specification, they can formulate properties that are naturally modeled as independent partial specs. These are concise, quick to write, and match the needs of NF operators and developers. Given a specific NF, most of the code in the software stack beneath will never execute. So Vigor automatically excludes such code from verification and thereby scales to the full software stack. That was theory, but does it work in practice? The two key questions is whether it indeed does not burden developers and whether it imposes any performance overhead on the verified NFs. To evaluate Vigor, we used it to implement and verify 5 network functions. a NAT, a load balancer, a traffic policer, a bridge with Mach learning, and a firewall. The human effort of verifying them is virtually nil. Once we verified the library, which took us about a couple of years. Verification with Vigor is fast enough to run on every code commit. Consider the NAT, for instance. The library is pre-verified, so we start with exhaustive symbolic execution that takes about 7 seconds and yields 54 symbolic traces. To stitch and validate such trace takes about a minute and a half. The trace validation is embarrassingly parallel, so on a 50-core machine, it takes less than 2 minutes to verify the NAT. If you have half as many cores, it will take 4 minutes. At this order of magnitude, one can verify the NF on every commit. Similar story for the full stack verification, except that here we are looking at the total verification time of hours instead of minutes. So we could run it at least for every release. During verification, we found bugs in our code in the DPDK packet aware framework and the NIC driver. We reported the bugs. Please see our paper for the details. Turning the corresponding RFCs and IEEE standards into specs took a couple of days each and requires tens of lines of Python. Partial specs start from a single line of code and can be developed in small increments. What about the performance? For a verified NF to be acceptable in practice, it must run no slower than an unverified one. We show that Vigor verified NFs perform on par with the fastest open source NFs we could find. On this plot, you will see round-trip latency in our test bed on the y-axis. The horizontal axis shows the different NFs we benchmark. No-op is a trivial NF doing no processing. In each group, there are Vigor NFs and baseline NFs. We compare two, they are based on click. The latency of Vigor NFs is on par with the baseline. It is even slightly better, and that is mainly because of the software stack of the Vigor. It is monolithic, so compiler can run a lot of static optimizations across the entire stack, back to the framework driver and OS. Being monolithic is not a problem because the entire code is formally verified. This graph shows in millions of packets per second the throughput over a 10 gigabit per second link along the y-axis. The horizontal axis is the same as before, and Vigor NFs also have competitive throughput. If we enable batch processing, we can improve throughput of some of the baseline NFs, but of course we'll degrade latency. In any case, our prototype does not support batching yet, but we'll still report the batching numbers in the paper, as well as the details of the experiments, but the conclusions are here. Verification with Vigor framework is easy and fast and can be a part of a continuous integration process. Writing full and incremental specs in Vigor is comfortable and quick, and Vigor incurs no performance overhead on verified NFs. To sum up, Vigor is a framework for no expertise required push-button verification of the entire software stack of network functions in a pay-as-you-go manner. In our view, that means that Vigor enables practical verification of software network functions. Thank you.
We have time for a couple of questions.
Hi, I'm Swati from UBC. Thank you for the presentation. I have a question about the eval section. The eval seems to cover only header processing network functions. So I wonder how well will Vigor scale with payload processing network functions such as application firewalls and L7 load balancers.
Sorry, could you repeat the packet processing network functions, or what you said?
Sorry. So the eval covers header processing network functions such as NAT and load balancer. So if you throw payload processing network functions such as application firewalls, how well will Vigor work with those?
So that's a good question. We've thought about it, and that's future work in supporting the full network functions that process the streams instead of packet headers, the packet content as well. This is easy to enable if you extend the library with the corresponding processing unit. So our framework is agnostic to how you process the packets, as long as you have the specific data structure. In your case, that's probably going to be a regular expression matcher that is formally verified and part of the library. Then you can process packets. You can process the content of the packets as well.
Thank you.
Hi, Mihai Budiu from VMware Research. Flow tables are finite in size. So what happens if you run out of space?
This is specified in our spec, and the limiting factor is not even the flow table size, but the space of the UDP and TCP ports that you can allocate. Those are quite finite, and if you run out of space, you have to drop the packet. Yeah, I mean, so you can pass the packet that going outside, but you will not create the connection.
Jay Lorch, Microsoft Research. Thanks for the talk. Great talk. What if in step 3, when they push the button and wait for a counter example or a verified, they find themselves waiting for a while? How do they know they're not going to be waiting for their entire lives?
So our verification process consists of 3 steps. The first one is done already, and you don't need to wait for it.
Just
the
step 3.
Symbolic execution part is on the conscience of the CLI developers. How they report process. This is we just reuse that. We don't improve the user experience in this part. And the last part is validation. Symbolic execution produces traces. So we have the number of traces, and each trace, as you've seen, validates within a couple of minutes. So you can track the progress of validation just by the counter of traces that have been validated.
Oh, so you have a guarantee of how many minutes it will take to produce a counterexample? You've solved the halting problem?
Sorry, can you repeat that?
Can you guarantee a number of minutes that they will have to wait, and they'll have to wait no longer for a counterexample?
We cannot guarantee that. In our experience, all the traces have taken just a few minutes each, and so when the verification goes on, you can track how what part of the possible execution scenarios have been checked, and you can estimate. So we don't provide you the ETA. We don't estimate this, but it's pretty trivial for a user to calculate when the whole thing finishes.
Last question.
Hi, my name is Won-Sum Young from KAIST. I am curious that what is a specific example of the spec, and your bigger check also memory safety?
So say it again.
Is bigger check also memory safety, such as there is no memory leaks or some segment parts?
Yes, we verify memory safety. We verify this functional correctness, and that cannot be done without the basic correctness properties such as crash free, the memory safety, and progress, liveness.
And also, I'm curious about that. What is the spec? I don't know what is some example of some specs?
What is the specification for memory safety property or for the semantics of the NF? Because so I've shown the specification. It is pretty short, but it can be a pain to read from the slide. Let me just find it quickly here. So this is a specification of a firewall. I mean, we can take it offline. You can read it closer because yeah, I understand it's small font, but it should be in the paper. 30 lines of code. Huh?
It should be in the paper. Just read the paper.
And yeah, it's well, it's if you go to the link vigor.epvel.ch, you'll find all the code and all the specifications. You can read, and you can even try it yourself.
Thank you.
All right, let's thank the speaker.